You know, when you think about what makes an AI truly smart, your mind probably jumps to massive data sets or, super fast computers. But what if I told you that some of the biggest breakthroughs are coming from a place you'd never expect? We're talking about pure, elegant geometry. Yeah, you heard that right. Today, we're going to pull back the curtain on a hidden mathematical idea that's making AI both way stronger and a whole lot smarter. Okay, so first things first, we've got to understand this central paradox in modern AI. I mean, these systems can do superhuman things, right? Like spotting things in photos way better than any human can. But they also have this secret hidden fragility. And that fragility, it leads to this really critical question. If these neural networks are so incredibly advanced, how come they're so easy to trick? What is this fundamental weakness that's lurking at their core? Well, the answer is this wild thing called adversarial perturbations. Basically, these are tiny, almost invisible changes made to an image or some other piece of data. To you and me, nothing looks different at all. But for an AI, these tiny little nudges can make it completely misidentify what it's looking at. And this isn't some random bug. It's a specific vulnerability that can be deliberately exploited. So, how in the world do we fix this? The solution, and this is the cool part, doesn't come from just throwing more layers or more data at the problem. Nope. It comes from geometry, specifically from the simple and incredibly powerful idea of being perpendicular. The fancy math term for this is orthogonality. Now, back in high school geometry, that just meant two lines hitting each other at a perfect 90-degree angle. But in the world of AI, it means something way more profound. It means two concepts, or two streams of information, are so perfectly distinct that they have absolutely zero overlap. Think of it like two radio stations on crystal clear channels. No static, no interference from each other whatsoever. We talk about ideas being independent all the time. But orthogonality? That's a much, much stronger guarantee. See, independent concepts might not rely on each other, but they can still get jumbled up and interfere. Orthogonal concepts, they can't. They're perfectly, mathematically separate. And look, this isn't just a nice little idea. It's a rock-solid mathematical theorem. When a set of vectors, which you can just think of as different directions in a data space, is orthogonal, it's guaranteed to be linearly independent. That's the highest degree of separation you can possibly get. And that right there is the key to solving our big AI problems. All right, so how does this geometric principle actually build a better shield for an AI? Let's take a look at how it defends against those sneaky adversarial attacks we were just talking about. So the problem really is that in a normal AI, the internal categories it learns are all crammed together. The line that separates, say, cat from dog is super fuzzy. And that's why one of those tiny adversarial nudges can so easily push the data over that blurry line and cause a big mistake. The solution is to build what's called an orthogonal classifier. By designing the final decision-making layer of the AI to be explicitly orthogonal, you literally force the maximum possible separation between every single category. This means the AI has no choice but to learn features that are truly distinct. And the result? A way more robust model that isn't so easily fooled. So orthogonality can make AI tougher, more robust, but its power doesn't even stop there. It also helps solve another, arguably even bigger challenge: how to train these truly massive, incredibly deep neural networks. This is a huge fundamental problem in deep learning. I mean, when you have a network with hundreds, maybe even thousands of layers, how do you make sure the learning signal, that crucial information about its mistakes, can travel all the way from the very end back to the very beginning without just fizzling out? Well, this is what's known as the vanishing gradient problem. Here's how it works. The network makes a mistake. A correction signal gets sent backwards. But with every single layer it passes through, that signal gets a little weaker and a little weaker. By the time it reaches those first few layers, it's practically zero. It's exactly like a message getting hopelessly garbled in a super long game of telephone. The early layers just stop learning. The solution, remarkably, is orthogonality all over again. It lets the network achieve this state called dynamical isometry, which is just a fancy term for perfect signal flow. By setting up the network's connections using orthogonal matrices, you make sure that the learning signal passes through every single layer without getting weaker or exploding. It's like a perfect relay race, where the baton is passed flawlessly from one runner to the next, no matter how long the race is. And the results are just incredible. Check out the blue line on this chart. With the standard methods, as the network gets deeper, the learning time just skyrockets. Now, look at the red and green lines. That's with orthogonal initialization. The learning time stays almost perfectly flat. I mean, a network with 100 layers can learn just as fast as a network with 3. That is a total game changer. Other methods, like the common scaled Gaussian approach, they can kind of preserve the signal's strength on average, but they totally fail to preserve its structure. The signal just collapses on itself. Only orthogonality achieves what researchers call dynamical isometry, preserving both, which is exactly why that learning time stays so flat. And this right here is a perfect picture of the goal. On the left, you see this tangled, messy internal state of a typical network. On the right, that's the ideal, a clean, diagonal, orthogonal system where every single piece is perfectly separated and efficient. That's what orthogonality helps the network achieve. So, let's pull all of this together. We've seen how one single fundamental concept from geometry, this idea of orthogonality, gives us this elegant solution for making AI both resistant to attacks and capable of learning at these incredible depths. It really just boils down to this. For the problem of vulnerability to attacks, we use an orthogonal classifier. For the problem of training super deep networks, we use orthogonal initialization. It's the exact same core principle, just applied in 2 different ways to get these incredibly powerful results. This is just such a beautiful example of how these abstract ideas from pure math can find their way into solving very practical, cutting-edge problems in technology. A single geometric principle, the simple idea of a right angle, is making our artificial intelligence both tougher and way more capable. And that kind of leaves us with one final thought. If a concept as simple as orthogonality can have such a profound impact, it really makes you wonder, what other simple, elegant truths from mathematics are just hiding out there, waiting to be discovered, holding the keys to the next great leap forward in AI?